All right. Theoretically, we should be going. All right. So, how's it going? Have a good weekend. Yankees won. My father-in-law is a pretty big Yankees fan. Well, my kids. The best way to watch a baseball game has to be the DVR. Just because they're so long. Anyway. You want to make a gazillion dollars, make yourself, go and design image processing software that can do, 3D virtualization of the strike zone and figure out whether or not that pitch really is a strike, dang it. Don't tell the umpire union you're doing it, though. Anyway, so questions. How's the lab cooking? Cooking? I really hope that you're done with everything except for the optimization by now, and if you're not, you're way, way not going to get done. All right, then. So, Lab 7, there's always Lab 7. Questions? I have concerns. We're going to need to have a midterm here sometime. So, I'm going to be out of town at the end of this week. I figured a good time to have a midterm would be when I'm gone. Just kidding. Tried to do that to my other class. They didn't like that idea. But anyway, we've still got probably. So Lab 8's a 2-week lab. Lab 7's a 1-week lab. So what I'm probably going to do is place the midterm during the first week of Lab 8. So this is the week to do Lab 7. It means next week's the first week for Lab 8. So, what about Lab 6? Like I said, you should be 90% done with Lab 6. And unless you're 90% done with it, well, you've got to think you're 90% done with it, because 90% done with it means you've only got one task left, and that last task is about 90% of the work. So anyway, we're probably going to have a test next week. Next week? That'll be about the right time. The end of next week-ish. Yeah, one of those two. It'll either be open book or closed book, one of the two. Take home or in class.
Is it going to be take home, X, or in class?
I usually give the second midterm in RTS as an in-class exam.
Usually everyone fails.
This is me. I mean, I've yet to have an exam where I haven't curved the score at least 30, 40 points. So, anyway, that's kind of where we're thinking. If you want to make this into a democracy, I'll take opinions on when you want to have an exam. Maybe we'll have a formal vote next time. So, anyway, you thinking about that? Okay? Hopefully by the end of this week, we'll have all the Lab 8 material finished, which is like 2 weeks ahead of where we were last year. So, I mean, we're cooking in lectures. I don't know what's going on, but we are moving right along. And it just keeps getting cooler and cooler stuff. So, we've laid off the book a significant degree this year, which is probably why we're moving along at a faster pace. It's not that the book isn't a good book. The book is definitely a good book, and we are going to have to rely on the book to a significant degree in Chapter 13. That's really the culmination of this semester, the culmination of the subject matter for this class, and really what differentiates a real-time operating system from a regular operating system. Because everything that we've talked about thus far You know, all it really is how computers really work, as opposed to this is a real-time system or a real-time kernel or a real-time embedded system. So all that what I've been teaching you to date really is just how do things really work down under the hood. And embedded systems people usually have to deal with stuff that's under the hood. But you don't have to worry about all of this stuff when you're doing typical desktop processing. So that's why we talk about it in embedded systems classes, because you need to know about it if you're dealing with embedded systems. However, Windows does the stuff that we've talked about thus far. You know, Linux does the stuff that we've talked about thus far. They do it in a much more broad and in-depth fashion than what we've talked about, but everybody's got semaphores, everybody's got context switching, everybody's got preemption, everybody's got interrupts. Okay? So what distinguishes a real-time operating system from a regular desktop operating system? It's not the fact that you can do preemption, and it's not the fact that you can do interrupts. It's the fact that it has to be designed with the knowledge that you are interfacing directly with its environment. And that impacts the design of the operating system in different ways, but the specific way that it has to impact the design of the operating system is the fact that when you're interacting directly with your environment, you have to get the operating system done and out of the way quickly, because the latency at which you respond to an external event can be very, very important and can be the difference between success and failure. And again, real-time systems has nothing to do with make everything go really fast. This class isn't about optimizing software. If you keep on waiting for us to get to where we're making software go really fast because it's got to be real-time, that's you're going to be sorely disappointed, because that's not what a real-time system is all about. A real-time system is a system where time is a factor in the correctness of the system. So the impact on the operating system is that you have to have the ability to interact with your environment directly, and you have to be able to do it in such a way that you can satisfy the timing constraints that which your environment imposes on your system design. The best that your operating system can do, since it's designed for multiple types of applications, is to not be a hindrance or an encumbrance on a system that has to have strict time constraints. So there's two ways in which time constraints impact the design of the operating system. Number one, the operating system let me not say that it's two ways. There are a myriad of ways that time constraints operate on it. One of the ways is that the operating system has to operate the same way every time. What we call this is determinism. Okay? So an algorithm that you write, that algorithm could, if you've got a whole lot of decision points inside your algorithm, different traversals of that algorithm or implementations of that, or invocations of that algorithm, you may traverse the path through it, through this statement, those statements, and this statement, or you may traverse through this statement, that statement, and this other statement. If the algorithm is behaving correctly, sure, you might have different paths through it to achieve some result. But the point is that it takes a different amount of time each time you run it. Okay? We don't like variance in the time that it takes our operating system to execute. We don't like changes to that time. The reason why is because we want to be able to predict how the performance of our system is going to be. We want to know if we're going to put this operating system into an application where I have got such and such timing constraint. I want to be able to prove that my system meets the timing constraint. If I've got this big question mark on my operating system of, I don't know how long this guy's going to take. Sometimes it goes quick, sometimes it goes slow. That's a big question mark, and I can't prove anything about my system implementation based on an operating system that has non-deterministic behavior. Okay? So this is where we start to diverge from the traditional operating system. The traditional operating system is designed to support high throughput of computation. You want to do a whole bunch of jobs, get all the jobs done, and get them done well, get out of the road, get on to more and more things. With a real-time operating system, we're not necessarily concerned with throughput. We are concerned with deterministic latency. So when an operating system goes and does something, we want it to take the same amount of time every time that it does it. Okay. Let's consider for a moment our priority queue. So we've got a linked list priority queue. And again, there's a divergence between what you're working on in the lab and what you're going to be working on in the lab and what we're talking about in class. So the stuff that we're talking about now is Lab 8 stuff, okay? You are finishing Lab 6. We've got all the material that we need in order to do Lab 7. That's all the semaphore business, okay? So we'll be posting Lab 7 so you can work on that. Lab 7, we introduced the idea of a priority queue where every process has a priority, and we're going to, on purpose, not be fair because we want to let the highest priority process win, okay? So the way that we're addressing the priority queue in Lab 7 is using a linked list. So we're going to have a linked list that maintains, I told you about there's two different ways. You can either have the linked list be a sorted linked list where you can figure out when you insert a process into this linked list, you can figure out where it should go as you insert it. So you gotta effectively maintain a sorted list. You gotta do a search on the insertion. And then to query the linked list, you just grab the guy that's at the top of the list and that's it. Or alternatively, you can, as you remove a process, you can search for the highest priority process that's in the list. But either way, either on insertion or removal, you've got an order n. Okay. So what that means is it about takes, in the worst case, or on average, depending on how you want to analyze this, but it about takes on the order of the number of nodes in the list in order to figure out what's the highest priority process. Or, on this approach, if you sort on insertion, it takes about that much time, about the number of nodes in your list in order to insert a node into the list. Okay. What the primary contention and what we claim as being evil is the fact that the execution time of your priority queue depends on the state of the queue. So if the insertion time is order n, then how much time does it take to insert a node into the list? Well, it depends on what n is. Where n is the number of nodes in my list. If I've got a 3-node list, it takes a lot less time on average to insert another node than if I have a 20-node list or a 500-node list. So the insertion time grows as the list grows. Likewise, depending on how the list is stored or the state of the list. So if you have if you're inserting a process that has higher priority than everything else in the list, and you maintain a sorted list, the time that it takes to insert that guy is going to be much faster than if you have to search to the end of the list in order to figure out where this process you're inserting fits. Okay? So even if you have a 10-node list and you're inserting a process, it could take a different amount of time depending on what the priority of the process that you're inserting is relative to the priorities of the processes that are currently in the list. Okay? So the time is not the same depending on the state of the list and the priority of the process you're inserting. So what we have is a variance here, and this is dude number one evil thing in real-time systems. Non-determinism. We don't like it. There are situations where we need to tolerate it. So I'm not going to. I don't want you to start thinking you have to eliminate every source of non-determinism in your application. That's not necessarily the case. If you have a non-determinism that's, like a nanosecond, well, that's in the noise. We don't care so much about that. But if you have non-determinisms that can range from, your execution time can go from anywhere from a microsecond up to 3 milliseconds, that range of non-determinism, that variance can be really, really bad. Okay? The non-deterministic execution performance of a desktop operating system is pretty large, as opposed to a real-time operating system. The real-time operating system, the only way that it's different than a desktop operating system is that it keeps the operations that the operating system performs short and deterministic as much as possible. Okay? So, and it also keeps the interrupts disabled for as little time as possible. Okay. So the point of our priority queue with our linked list implementation is that its execution time depends on the number of tasks in the queue. One more example of non-deterministic behavior. There are situations in real-time systems where you never want to do non-determinism. One of the biggest non-deterministic functions that you can use is freeze. So what you should never do in a real-time system, especially in operating system code, is call free. You can call malloc all you want, but you cannot call free. And you should never have a memory leak either. So, there you go. How are you going to fix that? So there are various ways, and if you had 3720, you had the opportunity of, well, Derek, I'm sorry. Your education was impacted by us not getting to the malloc lab at the end of that semester, but everybody else who had 3720 last year had the opportunity of rewriting malloc. So, of trying to rewrite malloc anyway. But you can provide, and real-time operating systems tend to do this. They provide an implementation of malloc that's deterministic and doesn't have the heap compaction, because it's this compaction operation that can take a whole lot of time depending on the fragmentation of the heap. So, never call free in a real-time system. What we're going to do is we're going to develop, I call this lecture Death by Lookup Table, and you'll understand why by the end. Good stuff. We're going to implement a deterministic priority queue. Okay? We'll call it table-based scheduling because we're going to use lookup tables in order to define this deterministic priority queue. Okay? So, this usually makes everybody's head spin. So pay attention. Not this part next, but the whole lecture. So I'll try to do the best that I can to try to make it as clear as possible. But this stuff is great. It's a lot of fun. You'll think it's pretty cool, but it takes some getting used to. Okay, so we're going to suppose that we have a maximum of 64 processes in our system. Why 64? Because the king decrees it so. Okay, it's good to be the king. 64 processes in our system. You remember we said we have every process has a priority and no processes share priority. Okay, so we're going to define an array called all processes that's indexed by the process priority that is 64 slots long. So all of our processes, this array is contains pointers to the processes. So all of our processes are housed or held by this all processes array. Okay, it's a 64 slot array of pointers to processes. Okay, and again, the all processes array is indexed by the task's priority. In some sense, we use the task's priority in a similar way to its ID. Okay, so now what we're going to do is we're going to create a table to implement the ready queue. So we'll do a type def unsigned char bool. So we're just going to declare a bool. Okay, we're going to use 0 and 1 to indicate readiness. 0 indicates the process isn't ready. 1 indicates the process is ready. Okay, so let's define an array called ready of type bool of length max processes. Okay. So we're just using an array instead of a linked list to state whether or not a process is ready. So it looks like this. So let's suppose that we have, so each entry in this array is a bool and it's got the value 0 or 1. If it's 0, then the process is not ready. If it's a 1, then the process is ready. So over here we're indicating that process 2 and 3 are ready by virtue of the fact that their entries in the table are 1s and everybody else is 0. So 64 slots in this array, processes 2 and 3 are ready, the table looks like that. We've thrown out the linked list. This tells us which processes are ready and which processes aren't. You like that? Good? We happy? Deterministic? That's a data structure, it's not an operation. It can't be deterministic. It can't be not deterministic either. Operations are deterministic, not data structures. Okay? So we have to figure out how do we figure out whether the highest priority process, or what is the highest priority ready process. So this is the question that we're asking. What is the highest priority ready process? So because our scheduler wants to query this table and see, I want to know who's the process that has highest priority that's ready to run. Okay. So I'm going to query the table and ask what's the highest priority process. So what is the answer to this question? I'm going to look at that table and I'm going to find out what's the index of the first asserted entry. Because the index of the first asserted entry, starting at the top, going down to the bottom, the index of the first asserted entry, that's the priority of the process that is ready. And then what I do is I take that priority that I find, which is the index into this table here, I drop that into the all processes array to get the pointer to the process that's ready. Okay? So find the priority of the process that's the highest priority ready process. So how do we do that? So I'm going to define this function called find highest that just contains a for loop. For I equals 0, I less than max processes, I plus plus. If ready sub I, return all processes sub I. Okay? So it'll just loop starting at the top of that array, go chunk, 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 chunk down until it finds the first entry in that array that says this is the highest priority ready process. As soon as it finds somebody that is ready, it'll return the index. So it knows that I is the index, then it drops that index into the all processes array, returns the pointer to the highest priority ready process. Otherwise, we're going to return null, indicating that there is no ready process. Okay, problem solved? How many of y'all say it's done? We're done. We're good. Considering the time, 5 minutes to 12, probably not done yet. How many of y'all see a problem with this? Tony, what do you see as a problem with this?
It's only going to run the first process. That's right.
Well, okay, under the assumption, so it'll only run the first process that's ready. That's correct. All that we're doing is querying the table saying, who's the highest priority ready process? And under the assumption that some other entity will be marking processes as not ready and marking processes that are ready. So all that we have to do is just figure out, given the table as it is, who's the highest priority ready process. It's up to the scheduler to decide whether or not to run them. Okay? What? It's still, okay, Brad says it's not deterministic. Why do you say it's not deterministic?
Because it has, if no process is ready, then you're going to go through all 64 steps.
Okay, so process 2 is going to run. How long does this code take to run? Assuming a compare takes a cycle. About 2 compares. 2 iterations of the loop. If no process with higher priority than process 40 is ready, how many units of time is this going to take to run? So is the execution time dependent on the number of processes in the ready queue? Depends on the state of the processes. Depends on where the highest priority process lies in that array. So if the highest priority ready process has a very high priority or a low priority number, then this will take much less time than if the highest priority ready process is farther down in the array. Okay? So it takes a different amount of time each time you run, depending on where the highest priority process resides in that array. So congratulations, we've thrown up the linked list because we didn't like it because it's not deterministic, and we've replaced it with a non-deterministic algorithm. Great. Spinning the tires. This must be like lab. Okay. So is it deterministic? Nope. Is it efficient? Well, let's look at the space efficiency of the algorithm. How much information are we storing in each slot of that array, of the array that we're doing the lookup of our, our priority queue array, of saying, is this process ready, yes or no? I'm talking about the array that, not the all processes array, but the array of bools that says, is the process with this priority ready, yes or no? 64 bytes. How much information does it take to state whether or not a process is ready? A bit. So we're using 8 times the information storage that we really need. So why don't we compact this guy to reside in and to store the state of a process in a bit instead of a byte. So let's suppose that we have a register. So we'll take a 32-bit register right here. There's 32 bits. We'll use 1 bit of this register for each process that we've got in our system. So bit 0 corresponds to process 0, bit 1 corresponds to process 1, bit 2 corresponds to process 2, and so forth. So we've got a 32-bit register right here. We could easily say, suppose we have a 64-bit register in order to cover all 64 processes in our system. Okay? So in this representation, what we'd have is bit number 2 and bit number 3 would be asserted. All the other bits would not be asserted because we are showing a ready queue that indicates that process 2 and process 3 are asserted. So instead of saying, what's the index inside this array of the processes that are ready, we're going to say, what are the bit indices of the asserted bits inside this register? Okay? So this is much more space efficient. How would you do a lookup on this one? So here's a nice little loop that we could say. So let's suppose that that register, we access it with a variable r. So let's say T is some temporary memory location. We're going to copy the contents of our ready register into T. And then we loop over here. Again, we're supposing this is just a 32-bit register. We could easily extend it to 64-bit. But for I equals 0, I less than 32, I plus plus, we just have this if T and 0x01, so this and is the bitwise and. So what we do is we mask off the least significant bit of T, and if that indicates that that process is ready, if that's asserted, then that means the process corresponding to the least significant bit is ready. So I indicates the bit position. So for I equals 0, the 0th bit, we check to see if the 0th bit is set. If the 0th bit is set, then we return all processes sub 0. If it's not set, then we shift T by 1 bit. Okay? And then we query bit 1, which is now in the 0th position. We see if bit 1 is asserted. If it is asserted, then we return all processes sub 1, and so forth. Okay? You like this? More space efficient. Is it deterministic?
Yes. Or not. It depends where your bit is.
Cover up that part that says it's not deterministic. Why is it not deterministic? So it still depends on what position is where is the highest priority process. Okay? What is this algorithm trying to do? Trying to figure out what the highest priority process is, yes. But how is it doing it? What are we querying? We are trying to find out the index of the rightmost asserted bit inside R. Okay? You got the answer. What's the answer? Wow. Tony likes death by lookup tables. Okay. So this is not deterministic. The reason why is because we're still having this loop that will terminate early if we as soon as we find out what's the rightmost asserted bit of that value, of that register R. It's more efficient. One of the downsides of what we're talking about is we've got to contend whether or not we are going to be more efficient with the implementation that we're going to provide. It will be deterministic, but efficiency is something you've got to explore. Okay, let's just examine for a bit. Let's put our thinking caps on and figure out, what is this algorithm really doing? Well, if we wanted to pre-compute the answer here, if R, this is our register that contains all of the asserted bits or not asserted bits indicating who's ready and who's not. If R has the value 0, in binary, it's all of its zeros, all of its bits are 0. That means there's no process that's ready. If R has the value 1, if we examine that in base 2, then all the bits are 0 except for bit 0. So if that's the case, which process is ready? Process 0. Computer engineers always count from 0. Okay? So the bit position of the rightmost asserted bit is the priority of the process that's ready, the highest priority process that's ready. If R is the value 2 in base 10, it contains the value 1, 0 in binary. So what's the rightmost asserted bit position? This is bit 0, this is bit 1, bit 2, that's bit 32. Okay? So over here, bit position 0 was asserted on when R had the value 1. For R equals 2, bit position 1 is the rightmost asserted bit. Okay? So process 0 is not ready, process 1 is ready. And again, so R contains this binary value, so 1 bit per process. It could have some random assignment of bits in there that's just indicating which processes are currently ready. So we just scan through this guy and figure out what's the bit position of the rightmost asserted bit. Okay? And that tells us, the bit position of that rightmost asserted bit tells us which process is ready. So if we go ad nauseum through that process, what we can do is make a table. So if we examine the value contained in R in base 10, we have this leftmost column here. In base 2, we have the middle column here. So All that this middle column here is just looking at what that base 10 number is in base 2. Okay, so this is the number that register actually contains. And then over here, this is saying what is the priority of the process that has the high, what is the bit position of the rightmost asserted bit, or what is the highest priority ready process. If the number is 0, I don't care, nothing's ready. Okay? If R contains the value 1, process 0 is ready. If R contains the value 2, process 1 is the highest priority ready process. If the value contained in R contains the value 3 or 1, 1 in binary, that means both process 1 and process 0 are ready. Process 0 has higher priority than process 1. So the highest priority ready process is process 0. Okay? If the value in R is 4, that's 1, 0, 0. That means 0 is not ready, 1 is not ready, 2 is ready. So the highest priority ready process is process 2. And we continue going on down the line. 5, 1, 0, 1, that means process 0 is ready. So what we could do is pre-calculate every potential combination of the bit values in R and cook up what is the highest priority ready process. So if we contain a table indexed by R to tell us what is the highest priority ready process. So let's suppose that table is called tab. Okay? So tab has the values that just contain this rightmost table. So 0 we're just using as the value for don't care. If the value of R is all zeros, then we don't care because nobody's ready. If it contains a 1, process 0 is ready. If it contains a 2, process 1 is ready. 3, process 0 is ready. 4, process 2 is ready. 5, process 0 is ready. And so forth. So we just enumerate the various values that correspond to various values of R. Okay? So then what we now can do is just say, if we want to query what's the highest priority ready process given this register R that has marked in it which are the ready processes, all I have to do is take R, dump it into tab, and then take the result of that, which will tell me the index into the all processes array. So all processes sub tab sub R, that gives me the pointer to the process that is the highest priority ready process. Okay? You like that? Is this deterministic?
Yeah.
Absolutely. Mitch, you're on the money this time. Okay. Are we done? How many of y'all don't like this? Anybody willing to take a stab at why they don't like this? Very large. What do you mean a very large lookup table? We got 1, 2, 3, 4, 5, 6, and dot, 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 dot. Can't be too big. How big's that lookup table got to be? How many different values can R take on? 2 to the 32. How many bytes does each entry in that table take? It's an unsigned int. Okay? So how many bytes is that? 2 to the 32 times size of unsigned int. Size of unsigned int on a 32-bit machine, 4 bytes. 2 to the 32 times 4. 2 to the 33, 2 to the 34. How much RAM do we need?
Number 0, so.
Need 8 gigs of RAM to hold that one array. Is that going to work on our PS7200 board with our 32 megabytes of RAM? We got a problem. We got a big, big, big problem because that tab array is just too darn big. We have deterministic execution times, but the table's too big. So let's suppose that we had 64 processes. We'd have to have a table that would be able to index 2 to the 64 slots. You want to have enough RAM for that one? RAM's getting cheaper, but still, that's pretty painful. Okay, lookup table is deterministic, but it requires too much space. So let's examine an alternate approach. What we're going to do in our alternate approach is we'll bust this up into a two-phase lookup. Okay? So to do this two-phase lookup, we're going to have 2 structures instead of 1 structure. So before we just had this 32-bit or 64-bit register R, what we're going to do is we're going to have 2 structures that implement the same task as what that R did. So we will have a table of 8-bit registers where in this table of 8-bit registers, we will still have 1 bit per process indicating whether a process is ready or not. And then we will also have a summary register, which is itself an 8-bit register that indicates whether or not a group of entries inside this table have a ready process or not. So I'll show you a little bit more what exactly this means. So by virtue of having these two structures, we can significantly shrink the storage requirements for our lookup table. So point number one. This point number one is the we will have a table of 8-bit registers. So this is our table. We're going to have 8-bit values. Okay. So we're going to call this table B. So B sub 8. So this holds 8. This is an array of 8 chars. Each char has 8 bits. Size of char is 1 byte. 1 byte is 8 bits. We're going to say that each entry in this array, each bit entry in this array, is a slot where we indicate whether or not a particular process is ready or not. So each one of these slots is labeled bit 0 through bit 7, bit 0 through bit 7, bit 0 through bit 7, bit 0 through bit 7. But we are going to map the correspondence of the index of each bit to a particular process's priority. So in B sub 0, we have 8 bits. The 0th bit of the 0th slot in the B array corresponds to process 0, process 1, and so forth, process 7. The B sub 1 has 8 bits corresponding to process 8, 9, and so forth up to 15. Then the B sub 2 is from here, from process 16 up to 23, and so forth down to process 56 up to 63 in B sub 7. Okay, so again, one table, 1 bit per process. This is still 64 bits, individual bits. We're storing it instead of one contiguous 64-bit register. We're going to store it as an array of chars. Okay? Does this make sense to you? So this is just 1 bit per process. The effective index of that process is the priority of the process that we're mapping onto it. Okay, our summary register is again 8 bits. And what we're going to do is mark one entry in the summary register corresponding to where our bits asserted inside our B array. So we're calling this guy A. So bit 0 covers bits 0 to 7. Bit 1 in here covers bits 8 to 15. Again, these are bits 0 to 7 inside the B array, bits 8 to 15 inside the B array. So if you note, the bit position inside A corresponds to the index inside B. So if you remember, B sub 1 covered the processes 8 to 15. If A's bit 1 is asserted, what we're saying is that there is a process with priority between 8 and 15 that's ready. Or in other words, inside the B array, there's got to be a 1 inside, some value inside B sub 1 is asserted, or B sub 1 is non-zero. Okay? So each bit position inside A corresponds to a row inside the B array, and if you have an asserted bit here at that particular position, then the corresponding row in the B array is non-zero. I mean, some process in that priority range is ready. One way you can kind of think about this is if you OR all the bits together on the row here, then at that row's index, the bit position inside the A array is asserted, or is equivalent. So if you OR all of these bits together on the 0 slot of the B array, A's bit 0 gets that value. If you OR all these guys together, A's bit 1 gets that value. If you OR all on row 7, all of those guys together, then A's bit 7 gets that value. Okay? So if all those values are 0, then that slot in the A register is a 0. If there is some bit that's asserted, doesn't matter if there's 2 of them, 7 of them, 1 of them, if there's any bit that's asserted inside the row inside B, then the corresponding bit inside A gets asserted. So if bit 3 in A is set, that means that at least 1 bit in B sub 3 is set. Okay. So, now let's look at our declarations again. Again, our type def unsigned char is a byte. We have byte A and byte B sub 8. So it says B is an array of chars, 8 slots long. How do you do a lookup? Well, option 1, you can use a for loop. We don't like for loops. So option 2, def by lookup table. So we will do a 2-phase lookup. Phase 1. Given the summary register, which entry in B has the highest priority ready? Indicates the highest priority ready process. Okay. So what we're going to do is say, well, let's suppose if A has the value 0, A again is the summary register. If A has the value 0, nothing's ready. If A has the value 1, that means that all the bits inside A are 0 except for bit position 0. Bit position 0 corresponds to B sub 0. So what that means is B sub 0 has a ready process. If A is the value 2, again in binary we look at that as 0, 0, da, 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 1, 0. So what that means is B sub 0 has no ready process because the summary register's corresponding bit is 0. B sub 1 has a ready process. Why? Because A's bit position 1 indicates that B sub 1 has a ready process. So what this is saying is that if this is a 1, 0 inside A, then B sub 1 has a ready process, B sub 0 does not have a ready process. Okay. Well, does that look kind of familiar? Isn't this what we were trying to do before? So what we're doing is we're going to develop a table that says what is the index of the rightmost asserted bit. So why don't we run into the same problem as last time? Last time we were trying to figure out what's the rightmost asserted bit of a 32-bit value. Here we're trying to figure out what's the rightmost asserted bit of an 8-bit value. If you have an 8-bit value, it can take on up to at most, or it can take on 2 to the 8 different values, or in other words, 256 different values. A 32-bit register can take on 2 to the 32 different values. The big difference between trying to have a lookup table that's 256 slots long and one that's 2 to the 32 slots long. Quite a large difference. So what we can do, we can actually use very effectively a lookup table that only has to range over 2 to the 8 different values. So we're going to define this as bit tab. So bit tab, the 0th entry in bit tab is -1 because that indicates nobody's ready and we don't care. So bit tab has the following entries: -1, 0, 1, 0, 2, 0, 0, 3, 0, 1, 0, 2, 0, 4, so forth. Okay, so Mitch is saying, wasn't BitTab declared as unsigned charge? I haven't shown the declaration of BitTab. So what BitTab contains is what's the index of the rightmost asserted bit. So it makes sense that it'd be unsigned, so you wouldn't be able to use the -1. But yeah, I don't know, from 37 to 20 days, it doesn't make any difference because it'll be FFFFFFF anyway.
So is that one of your indices from the valid index for the other table?
No. If you store this as an int, lots of f's, if you index an 8-slot array with FFFFFFFF, you're going to get a segmentation fault. So what the contention here is that BitTab over here, it only has 256 entries. We index it by some 8-bit number, and what BitTab tells us is what's the bit index of the rightmost asserted bit of that 8-bit number. This is effectively like a log2, okay, but just using a lookup table instead of actually invoking log2. So if we say BitTab sub A, that tells us what entry in B has the highest priority ready process. It returns an index into B, okay? So what we can do is figure out, we can use BitTab sub A to tell us where to look in the B array. So that tells us which of the 8-bit numbers inside B should I look for the index of the highest priority ready process. Phase 2 of the lookup, given the fact that we know which slot in B has the highest priority ready process, how do we determine which of the 8 processes covered by one priority band is the highest priority ready process? So option number 1, we could do a for loop and an index saying which of So if B sub 3 has the highest priority ready process, which bit corresponding to which process that B sub 3 covers is the highest priority ready process? Well, we could just for loop over all the bits in it, but we don't like for loops, so guess by lookup table. So suppose bit tab sub A returns 3. So what that would mean, suppose that A over here has 110110000. So by dropping A into the bit tab array, that's going to tell us what's the index of the rightmost asserted bit. The index of the rightmost asserted bit in this example is 3. So what that says is slot number 3 in the B array has an asserted bit. Slots 2, 1, and 0 do not. So B sub 3 has the highest priority process that's ready. So let's suppose that B sub 3 looks like 0, 1, 1, 1, 0, 1, 1, 0. What's the highest priority ready process? The highest priority ready process is the one that corresponds to the bit position that's rightmost and asserted. But if we want to find the index of the rightmost asserted bit of an 8-bit number, how do we do that? We're asking the same question here that we asked here. Okay? This is just an 8-bit number. All that we want to do is find out what's the index of the rightmost asserted bit. This is an 8-bit number. We want to find the index of the rightmost asserted bit. What did we do here to find the index of the rightmost asserted bit? We dropped it into bit tab. So down here we can do the same thing. We just reuse bit tab. Okay, B sub 3 represents the priorities 24 to 31. Bit 0 represents slot 24, or process. Bit 0 represents process 24, bit 1, 25, and so forth. Because bit 1 is the inside B sub 3 is the rightmost asserted bit, that indicates the process 25 is ready. So what we need to do is we need to do this conversion when we figure out what's the rightmost asserted bit inside the B array's correct slot. We need to convert that to the proper priority. So what we're going to do is drop in B sub 3 into bit tab to tell us what's the index of this 8-bit number of the rightmost asserted bit. So when we do that, in our current example that we're running right now, that'll return the value 1 because bit position 1 has a 1 in it. How do you calculate the priority number? You use the index into B. So it's 3 times 8. Why 3 times 8? This is just like multidimensional array addressing. So we're on the third row. The first row, row 0, covers 8 processes. The second covers 8 processes. The third covers 8 processes. So we've got to figure out how many processes that we skipped over and then add up an offset in this row of how many we're skipping over until we get to the right value. So 3 times 8 plus 1. Okay? So this is the index we used in the B array. That's just 8 processes or 8 bits per word plus 1 is the offset in the current 8-bit value that we're referencing. So putting it all together, the indexing goes IND equals bit tab sub A. So this is how we figure out what is the index into B that we're going to reference. Then to calculate the process ID or the priority, we'll take IND times 8 plus bit tab sub B sub IND. So that tells us the process's priority, who is the highest priority ready process. In order to access a pointer to that process, we just return all processes sub PID. That's deterministic. That'll fit on our processor. That's what you've got to implement for Lab 8. And you've got to implement insertion, and you've got to implement removal. And I'm going to show you about all that stuff as we go. But anyway, so I'll be quiet now, and we'll pick this up next time. I'm not going to have office hours on Wednesday because I got to go on a trip. So anyway, be ready for that.